All right, chemists, let's move on with our advanced theories of chemical bonding. So remember, we're learning advanced things. So don't be scared. If you've taken chemistry before, I feel like up until now, a lot of the stuff might have been kind of familiar, but now these next topics are a little bit deeper, a little bit more advanced, but I know you guys can handle it. You have a really strong foundation in chemistry because I've taught you thus far. So where we left off on Monday is we were talking about hybridization. All right, so the number of electron domains around our central atom is what dictates how many atomic orbitals we combine to produce that same number of hybrid orbitals out. The reason we need to hybridize is because if you think about the orientations of our orbitals, S, P, S and P orbitals, so like PX, PY, PZ, that's just the XYZ coordinate system. How do we get a trigonal planar out of just PX, PY, PZ? The thing is we can't just use pure atomic orbitals to get that shape. That's why we need to hybridize. So sp2, where we combine an S and two different p orbitals. The p2 means p squared, so there's literally two p's there. When you do a linear combination, you get the trigonal planar, 120 degrees, all fine and dandy. When you combine when you have four electron domains, combine four atomic orbitals to get sp3, that's a tetrahedral. So it's all consistent with Vesper theory, which is really nice. So once we make hybrid orbitals, right, so we can inspect our central atom here for oxygen. There's four electron domains because there's two bonds and two lone pairs. So four electron domains, we need to hybridize to make sp3, all right? So we need to combine three atomic orbitals to get us three hybrid orbitals. So the beauty that comes out here, right, the thing that amazes me is when we rearrange the 6 valence electrons on oxygen, all right, rearrange them in our hybrid orbitals, what comes out is something that reflects exactly what our Lewis structure says. So we have 1, 2, 3, 4, 5, 6 electrons here. So we see the two lone pairs that are on our Lewis structure, but we also see the two unpaired electrons we need to form covalent bonds with the hydrogens attached to water. And the great thing is that they're in the correct orientation to be consistent with valence bond theory. So the electrons on oxygen involved in this bonding are sp3 hybridized. What is the atomic orbital that's overlapping with this electron on hydrogen? What orbital? Where is this unpaired electron? I didn't quite write it out. I just treated hydrogen, its electron, as a dot, but it's not a dot. It exists in an orbital. What orbital is that electron in? 1s, that's it. All right, it's the 1s atomic orbital. And so that, it gives us the correct overlap to be consistent with valence bond theory. All right, that's what you see right here. See? Hydrogen's s orbital right there, 1s orbital, there's its electron, there's the other one, there's an unpaired electron in the sp cubed or sp3, and then hydrogen has its unpaired electrons, and then there are two lone pairs. So that's the beauty that comes out of that. So we did 4 electron domains. What if there are 5 electron domains around our central atom? We combine an s, a p, another p orbital, then another p orbital. Do we have any more p orbitals to play with if we want a 5th electron domain, a 5th atomic orbital? No. How many ml values are there for a p subshell? There's only 3. There's only 3 p orbitals. So once we get to an electron domain of 5, you would imagine that we have to add a new atomic orbital, and the next available kind would be a d orbital. This is a little bit controversial, but our system works really well here. If you read the book, there's a little blurb saying, like, you would think if we need 5 or 6 electron domains, we need to add a sp3d for 5 electron domains, spd2, meaning we have to add 2 more d atomic orbitals to get 6 electron domains. It works well within our kind of how we're approaching this, but technically from computations, it actually doesn't occur this way, but I'm going to show it to you anyway because I think it explains a lot of things. Because the idea is in order to get 5 or 6 electron domains, don't we have to expand our octet of our central atom, right? Like, so like phosphorus with 5 bonds to it. It would have an expanded octet. It would have 10 electrons around. It has to expand. What's the rule for expanded octets? What can expand its octet? Things that are period 3 or heavier. Once you're in period 3, you're close to what kind of orbitals? Where do our d orbitals start? In period 3. So like n equals 3, all right? So once we get to period 3, those d orbitals are more accessible and can accommodate those expanded octets. And our idea of hybridization kind of plays along with that. So here's the complete list of all the different hybridizations. It should look really familiar, all right? Where all of these different shapes and bond angles are the exact same as the electron domain geometries from Vesper theory. The only thing that we're adding here is the hybridization, but you can just figure that out by the number of electron domains. So it's simple as that. All right, and so yet again, 5 and 6 are controversial, but let's just do it anyway. All right, so PF5. So we go through the same process. We look at the central atom. You know, for fun, let's predict its geometry. All right, so it's 5 electron domains. So what geometry is 5 electron domains? Trigonal bipyramid, great. Are there any lone pairs to account for? No, there are not. So 0 lone pairs, so the molecular geometry is going to be the exact same. It's going to be trigonal bipyramid. It's going to have the axial position and the equatorial. All right, so based upon the number of electron domains, what's its hybridization? S, P, 3, D, and that's it. Right? Yeah, 1, 2, 3, 4, 5. Great. So if we were to draw the boxes for the hybridization, how many boxes would I draw? Would I have to draw? 5. 5 hybrid orbitals. So for fun, let's do that. Right, so that's 5 orbitals. That's my sp3d, 5 hybrid orbitals. How many valence electrons are on phosphorus? Let's look at the periodic table. There are 5. So I'm going to spread out my electrons. 1, 2, 3, 4, 5. So according to that hybrid orbital diagram, how many bonds, how many covalent bonds can that phosphorus make based upon the number of unpaired electrons? 5, is that consistent with the Lewis structure? Yeah, it is. It is, because there's 5 bonds, right, to phosphorus. There we go. That's where we get the electrons. That's how we spread them out. So if you think about, remember Lewis dot structures, when we drew phosphorus, I said, you know, we put them around kind of in a circle like this. All right, so according to the Lewis dot structure of phosphorus in that picture can only make 3 bonds. But we know phosphorus can expand its octet and make PF5, and so hybrid orbital theory here, which is, you know, consistent with valence bond theory, proves that PF5 can exist. All right, so let's keep going. BRCl3. So how many electron domains there? 5. So we have 5 electron domains, so 3 bonds, 2 lone pairs. So it's still trigonal bipyramid. That's our electron domain geometry. So I'm going to go ahead and draw that. All right, I'm going to draw it. Okay. But then how many lone pairs do I have to consider? 2 lone pairs, all right? So I'm going to draw those 2 lone pairs, but where are they going to go? Can I just slap them on anywhere? No, they go on the equatorial position on the belt. So I'm going to place 1 lone pair on the equatorial position and then place another lone pair there on the other equatorial position. So what shape is left when you cover up those lone pairs? T-shaped. T-shaped. So you don't really need to memorize the whole chart. Again, knowing the shapes via their electron geometries and placing the electrons in their appropriate place will get you there too. All right, so the actual question, hybridization of the central atom, we take the 5 electron domains and it ends up being the same, sp3d, all right? So the difference here, so sp3d will have the same number of hybrid orbitals, all right, for this central atom. So 5 boxes I'm going to draw, but how many electrons do I put in those boxes? 7, because it's bromine is my central atom. All right, so let's put 7. 1, 2, 3, 4, 5, 6, 7. What does that diagram tell us? Bromine has 2 lone pairs, and how many single bonds can it make? 3. What does the Lewis structure say? The same thing. Isn't that like eerie? Yeah, okay. All right, let's do the last one. BF5. BRF5, I mean. Okay, so how many electron domains? 6. So that is an octahedral, right? So I'm going to just go ahead and draw that. All right. So 6 electron domains, there's 1 lone pair to take care of. I can just place it anywhere. And so what you see when you cover up that lone pair, you're left with a square pyramidal. It has a square base pyramidal. Has a square base and then like a thing poking out to make it a square-based pyramid. All right. Do you want to draw the orbital? Oh, wait, we need to do the hybridization. 6 electron domains. What's the hybridization? sp3d2. So let's go ahead for funsies, draw the hybrid orbital diagram. How many boxes will I draw? 6. 6 boxes, because I combined 6 atomic orbitals. So I get 6 hybrid orbitals out. So 1, 2, 3, 4, 5, 6. Okay, great. But how many electrons do I place? 7, because it's bromine. 1, 2, 3, 4, 5, 6, 7. Is that consistent with our diagram or our Lewis structure? Yeah, it is. There's a lone pair shown, and then how many unpaired electrons to go ahead and make single bonds? 5. And that is exactly what the Lewis structure shows. Cool? Do we think that's cool? I think it's cool. Okay, all right. All right, so let's keep going. So let's do some exam type problems. All right, so here's a question. So I'm pointing to these different atoms. Identify what's the hybridization? Oh wait, yeah, what is the hybridization of these central atoms? So what's our strategy? You look at the central atom, you count what? Electron domains, and then you just mix that many atomic orbitals. So left to right, that carbon has 4 electron domains. So its hybridization is sp3. Right? So you would draw 4 boxes for its hybrid orbital. The next carbon is what hybridization? sp2, because there's only 3 electron domains. Remember, the double bond counts as 1. It's just 1 region of electron density. So 1, 2, 3, so 3 electron domains. And then that oxygen has how many electron domains? 4, because the lone pairs are also different electron domains, so that is sp3. Okay, great. So those are the hybridizations. You just count electron domains. All right, so that's a easier question. I'm going to ask in this next question, it's literally the same molecule, but I asked the question a little bit differently, and students, they think their heads explode. But I'm going to show you it's literally the same question. It's the same question. It's just asked a little bit differently. So this question is not pointing to the central atom. Note how it's not pointing to the central atom, but it's still the same molecule. I'm now pointing to the bonds between the atoms. And I ask what 2 orbitals overlap to make these bonds. And students' head explodes, and they're like, oh my God, I never learned how to do this. But you do. Right? So instead of, you have to remember valence bond theory. A bond is created when 2 orbitals overlap. So you just need to think, okay, what 2 orbitals are coming together to form the bond? So essentially, you're just telling me where is the unpaired electron on both atoms. So you look at one atom and you think, okay, what's its hybridization? And then you look at the other atom and you think, okay, where is its unpaired electron? What is its hybridization? But I will give an idea here that not all atoms need to hybridize. So like hydrogen doesn't need to hybridize. Chlorines, when they're on the end, or halogens don't need to hybridize. So let me show you what I mean. Okay. Do we remember what the hybridization of this carbon was? That carbon was what hybridization? sp3. So that's where the unpaired electron is on that carbon to form that bond. Where is the unpaired electron on this hydrogen atom? Let me just draw all those electrons. What orbital is that electron? An s orbital. So hydrogen, 1s. Those are the two orbitals that overlap to form that bond. You're just asking yourself, where is the unpaired electron? Where is it? What orbital is it? Because it's orbitals that overlap that produce bonds. So really, this question is no different than the previous question. It's no different. It's just we are stating two orbitals. That's it. All right, so let's move on to the next one. Okay, so this left carbon, we already said it's hybridization. It's sp3. What is the hybridization of this carbon? sp2. So those are the two orbitals that are overlapping. That's it. Okay, to form the bond. It's not that bad, right? It's not that bad. Okay, the next one, this bond. It's that carbon, we already got it. It's sp2 orbital is overlapping with what orbital on oxygen? Oxygen's sp3. So don't let your brain explode. Okay, and what about the last one? We already said oxygen is sp3 because there's 4 electron domains, but where is the unpaired electron on that hydrogen? It's in the 1s, so it's hydrogen 1s. That's it. That's it. All right. That's basically the concept, the theory behind valence bond theory. Its orbitals are overlapping. We need to think about where are those unpaired electrons? Okay, what orbitals are they in that are sharing that same space? Let me just change this question a tiny bit, this last one. What if I changed that hydrogen to a fluorine? What if I changed it to a fluorine? How would the answer change? It would still be oxygen's sp3 hybrid orbital, but where is the electron on fluorine? It's in its p orbital. Yeah, so it's fluorine. It's specifically its 2p orbital. We've looked at examples of this before where we had like HF or something like that, or HCl. All right, that we could use atomic orbitals to combine to make the appropriate shape, to say, okay, these are the unpaired electrons that are combining. They're in the right orientation for bond overlap. So when that fluorine or chlorine, it's on the end, we can use atomic orbitals just fine. But when we're talking about all other scenarios here, atoms that are in the center of the molecule, we typically have to hybridize. So that's one small little detail. Good? All right, so let's keep going. Okay, so the great thing is valence bond theory can not only explain bonding in the simple Lewis structures we talked about up there, but we can also use valence bond theory to explain more complex Lewis structures, things with like double bonds in them, and it works out beautifully, and I'll show you. So for fun, let's get the hybridizations going left to right. What is the hybridization of that carbon? sp2. Then the next one? Oh, fudge. There we go. Okay, sp2. What about the next carbon? sp2. All right. So in each of these, did I mix all of the atomic orbitals from those carbons? No. There's still some p's left over that aren't doing anything. So we will talk about those leftover p orbitals. What about in this triple bond? That first carbon is what hybridization? sp, and the next one is, also sp. So again, in this example where we have a triple bond, we're not actually utilizing all of the atomic orbitals in hybridization. So we will talk about what we do with those leftover p orbitals. They are actually involved in the pi interactions for double bonds. And so I will explain that using valence bond theory. So the next part of valence bond theory is let's use it. Let's think about orbital overlap to describe multiple bonding. So I mean, we're not just talking about single bonds, covalent bonds. We're now talking about double and triple bonds. Okay, and so I have to introduce a new explanation of orbital overlap. So I mentioned before that, like, you know, s orbitals can combine and overlap kind of in this head-on fashion, that like we can take s orbitals, right? Okay, from like hydrogen atoms, we bring them close together so they share this space. That's a covalent bond. Okay, we can also do the same thing with p orbitals. Doesn't this interaction look exactly the same as this interaction, right? Between the heads of those p orbitals, we have this head-on overlap. So that type of overlap, I just loosely or generically called that a covalent bond in earlier parts of this chapter, but specifically that interaction, this head-on overlap, is called a sigma interaction. Because it is in this head-on fashion where lots of electron density is being shared. Just trust me, it's called a sigma interaction. So in your head, just remember sigma means head-on. We can have it between s orbitals, we can have it between p orbitals, we can have it between an s orbital and a p orbital. They all look like this. Okay, that's the one type of interaction. The other type of orbital interaction we can have is weaker. All right, it's between these side-by-side interactions of adjacent p orbitals. That's what you see here, all right? We call this a pi bond. So let me undo the interaction. Essentially, we have a p orbital and another p orbital on another atom, and it's this interaction. It's weaker, but there's still this shared electron density across in between the two atoms. So this is a different type of interaction. We call this a pi interaction, all right, where they're side-by-side. So in your head, just know this is side-by-side, pi, head-on is sigma. And so the details here are that all single bonds are sigma interactions. But once we start making double, triple bonds, okay, when we think, oh, to make a double bond, it's 4 electrons instead of 2. But those 2 added electrons are actually not doing the same interaction as a single bond. We actually add the other component, a pi interaction. So what do I want to say? So a double bond has a sigma component and a pi component, a pi interaction. A triple bond is not 3 sigma components, it's actually a sigma and 2 pi components. And I'll show you where those arise from. So again, like a double bond is not 2 sigma interactions, it's a sigma and a pi. So we keep adding these pi interactions. And these pi interactions are between these adjacent p orbitals, unhybridized p orbitals. So let's talk about an example and how it all comes together. So I guess like the simplest example of a double bond would be a carbon-carbon double bond ethene. All right, so carbon-carbon double bond, there's 2 hydrogens attached to every carbon atom. So for fun, let's count how many total sigma bonds are there in this structure. How many total sigma? 1, 2, remember we have to count the single bonds. 1, 2, 3, 4. Are there any more sigma interactions here? A double bond is comprised of what? A sigma and a pi. So there's another one. So there's actually 5 sigma interactions. Okay. So you just have to remember, all single bonds are sigma. Double is a sigma plus a pi. And a triple is a sigma, a pi, and another pi. All right, how many pi interactions? Just 1. All right, so let's keep that in the back of our minds because we need to keep track of those electrons when looking at the electron diagrams. All right, so how we consider this, we're applying valence bond theory. So we want to look at each of those central carbon atoms. They have 3 electron domains. Vesper theory would predict trigonal planar. And so we know that each of those carbon atoms are sp2 hybridized. Do you agree with me? Yeah, 3 electron domains, sp2 hybridized. So if we draw the hybridization, if there's 3 electron domains, we combine 3 atomic orbitals to get how many hybrid orbitals out? 3. So that means since we only combined 3 of the atomic orbitals, we're left with 1. We're left with 1. It's left over. You see that it still stays there. It's still, part of the diagram. It's just it's not involved in hybridization. And so now we have this new sp2 hybrid set and this leftover p orbital. So what I'm going to do is just rearrange those 4 electrons that are coming from carbon into the hybrid sets. The p orbital here is a very similar energy as the hybrid set, so we follow Hund's rule here. All right, so that's what each of the carbon atoms have. So let's talk about where all of the electrons are. All right, so each of those carbons, you agreed with me, are sp2 hybridized. Both of them have electron diagrams that look like this, right? sp2 hybridized, we put the 4 electrons in, there we go. Let's keep track of every single electron. right? You already told me that in this molecule there are 5 sigma bonds and 1 pi bond. Let's see if we can't find them. So when we think about the sp2 hybrids, each carbon atom is trigonal planar. There's an unpaired electron in each of these. So look at these interactions. There's a sigma interaction. There's a sigma interaction. There's a sigma interaction. So if we keep track of what that carbon atom is doing, what bonds is it making, we see that this carbon atom is making a bond with hydrogen. Its unpaired electron is making a bond with hydrogen. It's making another bond with hydrogen with its other unpaired electron. But what is the last? What is the third electron doing? Keep track of it. It's making a bond with, is it another hydrogen atom? No, we're making a bond with the other carbon atom. All right, so we're making a bond here. So there's your carbon-carbon sigma interaction. It's the first component. So let's look at the other carbon. What are these 2 electrons doing? So look at this carbon. What else is it doing? It's making bonds to the hydrogen atoms. All right. So these electrons are making bonds to hydrogen. So I just want to make sure we take inventory of every electron. All right. So those are a lot of our sigma interactions. All right. So if we count it, how many sigmas are there? That's a sigma interaction. 1, 2, 3, 4, and then 5 sigma interactions. Great. We didn't touch these electrons. What do you think these electrons are doing? What orbitals are those electrons in? P orbitals. P orbitals, all right, on adjacent atoms, when they're out of the plane of the internuclear axis, they are involved in the pi bonding. So it's these electrons are involved in the pi bonding of the molecule. And that's what the picture is happening down here. So these black lines indicate the sigma framework, all the sigma bonds that we just went over. So this pi interaction is actually occurring above and below the molecule itself. All right. So these 2 p orbitals are on the z-axis, so it's perpendicular to the molecule itself, and it's in that side-by-side overlap. And so I want you to recognize that, hey, we have unpaired electrons there. Bonding is occurring, but because of where those electrons originate from, it's a pi interaction. And that's what gives us our sigma and pi interaction in our carbon-carbon double bond, because we know a double bond is a single and a double bond is a sigma and a pi interaction. Right, so we need to think about orbital shapes and how they're overlapping in space. This is a tough concept. It's a tough concept, but if you can keep track of hybridization and what your electrons are doing in terms of like where is it making its pair, what kind of orbital, hopefully it'll make more sense. Let's look at some more examples. Okay, so I just want to reiterate the difference between sigma and pi interactions. Sigma interactions, it's that head-on, end-to-end overlap. So here are some examples of a bunch of ways you can get it, all right? It can be between s orbitals, it can be between s and a p orbital, or even 2 p orbitals. In the previous example, we had an s orbital and a hybrid orbital also makes sigma interactions. This is the same type of head-on overlap in interaction, right? This type of interaction. A trick is that all hybrid orbitals will always sigma bond. Okay, that's a small little trick. It's because with pi bonds, the only way to get pi bonds in this class is through unhybridized p orbitals. That's the only way you can get it. It's the only way you can get it. To get that side-by-side interaction. It has to be unhybridized p orbitals on adjacent atoms. All right, and so the electron density will be above and below the internuclear axis itself, so out of the plane of the molecule. All right, so those are sigma and pi bonds. So sigma, pi side by side. Okay, so and then again, single bonds are all sigma interactions, so that the head-on, and once we make double and triple bonds, now we just start adding pi interactions. So a small detail I mentioned is that pi interactions are inherently weaker. This type of interaction, much stronger, much more overlap than this side-by-side. It's much weaker interaction. So we actually kind of see that phenomena through measured bond enthalpies, because, you know, if you just kind of guessed, you know, if you're given the single bond bond strength, so 346 kilojoules per mole. And I asked you, okay, estimate what you think a double bond, how strong a double bond would be. A reasonable guess would be just doubling this number, right? Like that's what a reasonable guess would be if you wanted to guess the strength of a double bond. It doesn't quite double. When we actually measure it, we actually don't see a quite exact doubling effect of a single to a double bond, and that's because when we go from a single to a double bond, we're adding a pi interaction, not another sigma interaction that's quite strong. We're adding a weaker component. So that's why we don't see a true doubling effect. And then same thing when we go to a double to a triple bond, we're adding a pi interaction to make that triple bond. So we see the bond enthalpy increase, yes, but not quite like a tripling effect. You see that? So that's kind of the consequence of the difference of orbital overlap that's happening with sigma and pi bonds. So if you're clever, okay. Sigma is a Greek letter, right? I'm not Greek, but like that's a Greek letter, right? I'm real bad with Greek letters. Sometimes I have to Google it still, okay? And I have a PhD and I have to Google it. Sigma is Greek for the letter S. S orbitals make sigma interactions, okay. Pi is the Greek letter for P. P orbitals, they do pi interactions. Okay, great. All right, so I have a moral to this, I promise. So we did a single, a double, a triple bond. What do you think 4 bonds is called? 4 bonds. Quadruple, right? Quadruple bond. Whoops. A quadruple bond. Right? 4 bonds. So 8 electrons total, right? So let's think about this. Let's think about this. What interaction do you think we have to add to go from a triple bond to a triple bond to a quadruple bond? I think a student might say, oh, another pi interaction, maybe. That's like a good guess, but let's think about it. When we, hybridize and stuff, we have like our S. Oops, that's too many orbitals. Too many orbitals. Okay, we got our P orbitals, right? P orbitals there. When we think about, okay, if we have like a linear molecule, it's sp hybridized. That first p orbital is that first pi interaction. The second p orbital is the second pi interaction. So can we make a third pi interaction? We can't. We can't. So what's the next available orbital that there is? Atomic orbital. Not a p orbital, but a d orbital. Okay, great. Do you think d orbitals make pi interactions like this? No. So what do you think? Using your scientific knowledge of the Greek alphabet, what kind of interaction do you think happens between d orbitals? Not pi, but delta. Yes, delta, because delta is the Greek letter for D. That's actually exactly what I studied in my PhD thesis. If you Google it, if you go to the library and Google my PhD thesis, it's like entitled, I studied and synthesized molybdenum quadruply bonded complexes, right? Where the first bond, or the first interaction in a quadruple bond is sigma. The second one is pi. The third one is also pi, but the fourth one is called delta because it's between d orbitals. So you might be asking what a delta bond looks like. Sigma interactions are like this. P or pi interactions are like this. A delta bond is between d orbitals. A d orbital looks like a butterfly, right? And so it's like 2 butterflies kissing, like this. That's what a delta bond is. It's really weak. It's really weak. And so these compounds were very highly colored. That's why I liked studying them. Okay, so that's just to kind of prove to you here that, the pursuit of knowledge and research, you're kind of at the cusps of human knowledge, delta bonds. But now you have the foundational knowledge to understand it. So you could probably understand some of my PhD thesis. Yeah, okay. You can look it up if you want. It's on the OSU website. All right, so let's go back and think about more hybridization, but let's go back to sigma and pi interactions. That's fine for us. All right. So let's look at formaldehyde, and let's keep track of all of the electrons that are happening here. So formaldehyde, we're going to focus on the carbon and the oxygen. What's the hybridization of carbon? sp2. What's the hybridization of oxygen? sp2. So I have that here, all right? So if it's sp2, there's an unhybridized p orbital on both of them. So let's place the electrons. How many electrons do I place with carbon? 4 valence electrons. So let's put the 4 in. So 1, 2, 3, 4. Remember, follow Hund's rule. The unhybridized p orbitals are the same energy as hybrids. All right, how many electrons to place for oxygen? 6. Did I just guess? No, it's on the periodic table. Hope you know that by now. So 6 electrons. So 1, 2, 3, 4, 5, 6. Okay. So these are sp2s. Okay. All right. So let's inspect what's going on. So I'm going to draw my molecule over here so we can see it over here when I zoom in. So let's look at the carbon atom. How many sigma bonds? So let's label every bond. What kind of interaction is this bond right there? Sigma. What about this one? Sigma. What about the first component of the double bond? Sigma. Then the second component? Pi. Okay. Let's see what happens here. All right. So according to this diagram, how many, look at the number of unpaired electrons. How many bonds can that carbon make? How many sigma bonds? 3. 1, 2, 3 bonds. So let's look. There's 3 sigma interactions that carbon is doing. One of those electrons are going to make a bond with hydrogen. The other unpaired electron is going to make a bond with the other hydrogen. And that third electron in the sp2 hybrid, remember it's trigonal planar, is making a bond with what? Oxygen. A sigma bond with oxygen, because that's what we labeled that bond as. All right, let's look at oxygen. In the hybrid, how many sigma bonds can oxygen make, according to the hybrid? Can these electrons do bonding? No, they're paired. So really, this oxygen can only make one covalent bond. So here is the sigma interaction, all right, on oxygen. Actually, it's bonding with what? It's bonding with carbon. It's bonding with carbon. These are the 2 electrons. I should erase that, all right? Those 2 electrons on carbon and then carbon and 1 on oxygen, that's making the sigma bond, right, between those 2. And then what are these electrons doing? What are those electrons doing? These electrons are making the pi interaction between carbon and oxygen. So this bond right there, because remember, pi interactions can only be produced by unhybridized p orbitals, electrons in unhybridized p orbitals. All right, so that's how we took track of all of the electrons. Actually, I didn't keep track of all the electrons. What electrons did I not say yet? The ones on oxygen. What are those? What are these paired electrons? What are those? Those are the lone pairs on oxygen. The lone pairs on oxygen, and from this we can tell that those oxygens, the lone pairs are in the trigonal planar arrangement, that all of those bonds are 120 degrees, plus or minus some deviations, but because we know that they originate from hybrid orbitals, they should be 120 degrees, right? So that's how kind of all of those ideas come together. So this is what that diagram shows. Here are our sigma interactions, all right, between carbon and hydrogen, the hybrids on carbon and hydrogen. There's our sigma bond. Oh, it already says it there. Sigma bond on between carbon and oxygen. There's the non-bonding electrons that we placed in the hybrid orbitals, and then above and below the molecule, there's our pi interaction from the 2 electrons that are in unhybridized p orbitals. So there we go. That's kind of putting it all together. So that's the great thing about valence bond theory. I love valence bond theory. It explains so much. All right, let's look at another example. Acetylene. So a carbon-carbon triple bond. So a triple bond has how many components? It has a sigma, a pi, and another pi. So let's study it. So each of these carbons have how many electron domains? In a carbon-carbon triple bond, has 2 electron domains. So what's its hybridization, each of those carbons? sp, yes, and that's what I have down here, over here. So there's one carbon, there's another carbon. Both of them are sp hybridized. Let's make sure we can't keep track of all of those electrons and what they're doing. So if we look at the leftmost carbon, all right, we have a sigma interaction with hydrogen. There's a single bond here. All right, so this first electron in the sp hybrid is making a bond, a sigma bond with hydrogen. And basically the other carbon atom is doing the same thing too. Right, they're both making sigma interactions with the adjacent hydrogens. Those are both sigma interactions, right? But we said that the triple bond is a sigma, a pi, and another pi. So which one of these, all right, because we have a bunch left, which set of electrons is making the sigma bond in the triple bond? Is it yellow? Is it yellow, pink, or green? Which one is the sigma component of the triple bond? Yellow, pink, or green? Remember, pi interactions can only be formed by what kind of orbitals? Unhybridized p orbitals. So that means these unhybridized p orbitals, these are the ones that are making the 2 pi interactions, these 2. Right? Remember, these are the bonds happening between the 2 carbons with the triple bond, right? So these 2 are the pi interactions. So the yellow electrons that I've highlighted is what interaction? There is my sigma interaction, all right? And so when we think about it, okay, so this is what the picture is down here. The yellow lobes, those are the large lobes of our hybrid orbitals. See how it's the head-on overlap that we're accustomed to with sigma bonds? And so what we have here are 2 sets of p orbitals, one within the x-axis and one within the y-axis. So one of the pi interactions is in this orientation. The other one is in a different plane because p orbitals, we have px, py, pz. Pz is involved in the sp hybrid, but x and y are in different planes, and so we have pi interactions in different planes. And so that's how we get our triple bond. So basically, in order to get a triple bond, you have to have an atom that is sp hybridized because you need to have at least 2 unhybridized p orbitals to be involved in our pi bonding. All right, so that's taking inventory of all of the electrons and what, where all of them go to make these Lewis structures and the specifics of the orbital overlap involved in bonding. All right, so that's acetylene. So let's look at one more example about orbital overlap, pi interactions, and hopefully this will fully explain resonance and what it is, not just guessing, oh yeah, smear that double bond around. Let's actually think qualitatively what that means, and it actually has to do with p orbitals, smearing, the whole smearing of electrons around. It's actually smearing it around p orbitals. So let's look at our prototypical resonance structure, benzene, where we have 6 carbon atoms and they're alternating single bonds and double bonds. So remember, benzene can undergo resonance because the idea is I can, place the double bonds alternating starting here or here. And so what we see with benzene is that those double bonds are kind of smeared around the whole molecule. We don't see short, long, short, long. We see all bonds with a bond order of 1.5 for those carbon atoms. So we don't actually see a discrete, double bond. It kind of exists everywhere. So what I want us to do is let's just focus on one carbon. Let's look at that one. What's its hybridization? sp. sp2, right, because there's 3 electron domains, right? Okay. So how many, let's look at the carbon atom, how many sigma interactions are attached to that carbon atom? There's a sigma there, there's a sigma there, and the first sigma is in the double bond. The second interaction in the double bond is pi. So that carbon atom is doing 3 sigma interactions and a pi interaction. So let's see if the hybridization, the electron diagram matches that. So sp2 is 3 boxes with a p electron on the outside. Carbon has 4 electrons, 1, 2, 3, 4. So hopefully you can see that these 3 electrons, these ones, are the ones that do the 3 sigma bond interactions. And then that 1 electron in the unhybridized p orbital is involved in the pi interaction on that carbon atom. We see it? And so every single carbon atom in this structure has that. They're all identical. So look at this carbon. 3 electron domains, right? This carbon, 3 electron domains. That carbon, 3, 3, 3. So every single carbon is sp2 hybridized. All of them have 3 electrons in its hybrids, 1 in its unhybridized p orbital. So let me show you the consequence of that. And that's down here, okay? So this framework shows you all of the sp2 hybrid interactions, all of the sigma bonds. The sigma bonds is what makes the ring. It's what makes all the bonds to hydrogen. It just makes the skeleton structure of the molecule. That's not the important part, okay? We need the sigma bonds to actually form the molecules. What I want you to think about and inspect here is that we have electrons in unhybridized p orbitals, right? On each carbon, right? Each carbon has this going on, this orbital going on. And that's what this B picture is trying to show. Each carbon atom in the hexagon has this p orbital that's perpendicular to the internuclear, plane here. All of those p orbitals have unpaired electrons in them, like this. All of them. So what do you need? What do you need to make a pi interaction? You need 2 electrons in unhybridized p orbitals, right? 2 of them. So if you were this electron, if you were that electron, would you make a pi interaction this way? Or would you make it that way? Or would you do both? Both, yeah, because the idea here is it's equally likely for that electron to do a pi interaction to the left or the right, so it does all of them. And that's what hybridization is, that what we don't see are localized pi bonds. We don't see that because it's equally as likely that electron will make the interaction this way or that way. So we do not see this. We don't see the alternating double bond, single bond, double bond, single bond, double bonds. We don't see that. So what we see instead is that all of these p electrons are delocalized across the entire ring. Right? So total, there are 6 electrons involved in this delocalized pi system on benzene. That those 6 p electrons across the entire ring are involved in what we call the pi system because it's spread across the entire ring and nothing is localized. And this is why we see 6 carbon-carbon bond lengths that are all the same length instead of seeing a short, long bond, because those the pi interaction is spread across the entire molecule. So whenever you see resonance, okay, resonance structures, what you're actually seeing is delocalized pi or p electrons. That's really what it is. Yeah, right. And so that consequence will come up in organic chemistry when you look at mechanisms, because oftentimes when you can spread electron density around a molecule, that oftentimes stabilizes the molecule. Right? That's more favorable to spread a negative charge across a large area than have it really localized in one spot. That's not super stable. Okay, all right. How do we feel about valence bond theory? Do you feel real smart? Feel real smart? Okay. Valence bond theory, it's beautiful in that we apply concepts of Lewis structures, Vesper theory, all right, and then adding the idea that, electrons, they exist in orbitals. In order to make a bond, electrons in their orbitals need to overlap and share the same space. And it's all consistent with all of the other theories we talked about before, all right? So these are basically the hardest chapters, sections, especially this chapter, that you'll encounter. And I think for most of you, it's because you've never seen it before. How many people have seen this before? Okay, like one, all right. Maybe they read the book, I don't know. You could technically, if you read the book before coming, then you've seen it before. So this next part of the chapter is the hardest theory. The most advanced theory, okay? It's the idea, when we were back in chapter 6, we treated electrons as dots, particles. We then thought of electrons, they exist in orbits, the Bohr model, right? Orbitals. And then we went to what? We went, electrons are waves, okay? So now we have to apply the wave nature of electrons, but we also have to keep in our back pocket that orbitals overlap in space, so we need to think about valence bond theory. We need to think about, I think those are the things we need to think about. So wave nature and orbital overlap. So we're going to talk about molecular orbital theory now, meaning orbitals that arise when we make molecules, meaning that we're combining atoms. Okay, so here's an example of, you get this on the exam, this nifty diagram. You've seen it on the first page of the recitation. I will go through what it means and how to use it, okay? It's not that bad. And this is a typical exam question, all right? So it says, apply molecular orbital theory and identify which of the following molecules is paramagnetic, meaning diamagnetic means that everything's paired. Diamagnetic means everything is spin paired, all right? And so, I know you don't know how to do this question yet, but hopefully you recognize, okay, there's a B2 molecule. I'm going to use this diagram because that's for B2, right? Or this is, the lithium's a weird one. You don't need this part of the diagram. Diatomic nitrogen, you would use this diagram, all right? Diatomic neon, you would use this diagram. So hopefully you recognize that. Now, so I will go through what all of this means, but do know that you do not need to memorize this table. You just need to know it means because you will be given this exact one. But so note that nothing's labeled on it. All right, so let's go. All right, MO theory. So let's tell the story of the electron. So in Lewis structures, we treated electrons as dots. There's a bond, right? Two unpaired electrons. They come together, they share, they form a bond. That's Lewis structures, the simplest, the beginning of, this chapter, this section. Then in valence bond theory, we got a little bit more sophisticated and we said, those unpaired electrons on each of those hydrogen atoms, they exist in orbitals. Specifically, they exist in 1s orbitals. And we just said, okay, you bring them close together, they overlap in space. That overlap right there, that's a covalent bond. Specifically, it's a sigma bond. That's valence bond theory. Okay? So now, in molecular orbital theory, we're treating electrons as waves. So we are considering the wave function of an electron. So waves, they can combine. When you combine two waves in space, they can combine constructively. All right, so if you have these two waves, okay, and they combine, you will increase the amplitude of the resulting wave, right? That's constructive interference. That's the first one, right? So this picture I'm trying to show you, in these examples, we have two atoms combining. In these examples, it's the same thing. I'm just showing you two electrons on two different atoms that are combining. We get a amplitude increase, and so what we call this a bonding orbital because the amplitude increases, that we are combining the two wave functions of the electrons, and we're making a new molecular orbital that's not only stronger, but lower in energy. All right, that's constructive interference. Okay, waves can add up constructively. They can also add up destructively. So if I just copy those waves here, all right, and I change their phasing, so see here in this example, the peaks, crests line up, but if I just kind of offset the phasing of the wave function of the first electron and the second electron, these two waves would cancel out. And we call that an antibonding molecular orbital. It's a molecular orbital because we're combining two atoms' waves. All right, and then the last type of molecular orbital is a non-bonding. Molecular orbital is just not involved in bonding. You don't have to worry about that. We just care about bonding and anti-bonding orbitals. Anti-bonding typically has that star next to it. So we call it like, we'll call an orbital sigma star, meaning anti-bonding. So star means anti-bonding, all right? Okay, so MO theory is the most advanced of all of the theories because we're working with the wave functions. We're working with literally the true nature of an electron, and it can explain a lot of things that valence bond theory cannot explain. But the beauty of it is it's consistent with everything we learned so far. It just layers on the difficulty, but it's still consistent with everything. So things that MO theory can do and why we care. We will learn a new calculation of bond order. That's a lot more sophisticated. We can predict whether a molecule will exist or not using this theory. We'll also look at magnetism, so how substances respond to an electric or magnetic field based upon unpaired electrons. And then finally, you'll talk about this in Chem 1220, but you can predict colors of compounds based upon MO theory as well. That was the nature of my work in my PhD. Why my compounds were so colorful were because of the MO theory behind the molecule. So, all right, so let's construct these. Okay, remember, electrons are waves. So when we combine atoms and their electrons, we combine their electrons, we combine their waves. So we need to think about constructive, deconstructive interference. So, okay. So the big thing with these diagrams, when you see MO diagrams, the boxes that are on the outside are always the atom. We're always combining two atoms. So what you see here is a hydrogen atom and another hydrogen atom. What you'll see in the middle will be the molecular orbitals, because when two hydrogen atoms come together, you make a hydrogen molecule. You make H2. So that's what you'll see in the middle. So if we think about these electrons, they're in boxes right now, but the box says it's in a 1s orbital, so that's what you see here. All right, we have a 1s orbital and another 1s orbital. Okay, if you think about those 1s orbitals coming together, if they're in the same phase, they add constructively, and we get this stabilization. We get this stabilization of the resulting molecular orbital. All right, so we get a box when there's constructive interference that's lower in energy than that of the atoms. So it's more stable to put electrons in this orbital than in this molecular orbital than the atoms themselves, right? And so that's what you see here: two atoms, s orbitals coming together in the same phase. They overlap in the same phase, and we get this nice sharing of electron density between those two nuclei. So for fun, let's look at these two. What kind of interaction is this? Sigma, yeah, it's the head-on overlap. So if we want to be super specific here and describe what this molecular orbital is, we call it a sigma orbital between 1s orbitals, so we call it sigma 1s. That's how we explain the whole thing. All right, so that's half of the diagram. Let's go. So we talked about phases are the same. Well, what if the phases aren't the same? What if the phases aren't the same? That's the next part, all right? So if the phases aren't the same, so I need to redraw the bottom of my diagram. That's my sigma 1s. So if the phases are not the same, the waves cancel one another, destructive interference. So that's what this picture is trying to show. One is a plus phase, the other is a minus phase. They combine. What kind of overlap interaction is this? Just think about it. A sphere coming together with a sphere. Don't think about it too hard. It's still sigma, but it's sigma, a sigma interaction, because the orbitals are out of phase, it's antibonding. So we call this new orbital that's higher in energy sigma star. It's still a sigma interaction because the orbitals are doing head-on, but because the phases are opposite, it's now a star, and it's higher in energy. All right, so that's the other side. All right, so there's our sigma star, specifically 1s, because it's occurring It's being produced by 1s orbitals, all right? And so what a antibonding orbital looks like. So let's compare the antibonding orbital here, you see this, versus the bonding orbital. The sigma bonding orbital puts electron density between the atoms, so that strengthens the bonds, versus the antibonding orbital. We have a node, okay? So like this plane where electron density does not exist between the molecule. So if you put electrons in this type of molecular orbital, you weaken the bond because of that node that is present, all right? That you weaken that bond, all right? So here, electrons in antibonding MOs will destroy or weaken your bond. So there we go. There's our molecular orbital diagram. So putting it all together, this is what it looks like. All right, so there's our hydrogen atom. So this is what I mean. We have our atoms on the outside. So atom 1, atom 1, atom 2. And in the middle, we have our molecular orbitals because this is our H2 molecule, atoms on the outside. On the bottom, we have the sigma bonding orbital because the phasing is correct to have constructive interference, while the top orbital up here has deconstructive interference. That's our antibonding orbital. So I already have it written here, but let me just go back up to this slide here. So I have my atoms, but what I haven't done is redraw my electrons in the middle, in the molecular orbital. So what you want to do is you want to add up all of the electrons coming from the atoms and then replace them in the new energy ordering following all our rules, Aufbau's principle, Pauli's exclusion principle, Hund's rule, things like that. We just refill them. So how many electrons should we place in the middle? How many electrons does diatomic hydrogen have? 2. Yeah, so we're just going to replace those 2 electrons. So I'm going to put my first electron there. Where does the next one go? Spin down. That's it. Yeah, so it's filling just like we did before. It's just now we kind of go bottom to top. That's it. All right, and so this is where our new, and that's what's down here. I wanted to show that, okay? Our new bond order calculation. All right, our new bond order calculation is specific for molecular orbitals, where we count the number of electrons in bonding orbitals minus electrons in anti-bonding orbitals divided by 2. This is our new calculation. It's only used for MO theory. So in diatomic hydrogen, how many electrons are in bonding orbitals? 2, right? 2 of them are in sigma 1s. How many electrons are in antibonding? 0. Okay, so 2 minus 0 over 2 is 1. So that means the bond order in diatomic hydrogen, according to MO theory, is 1. What kind of bond is that? A bond order of 1 is a single bond. Is that consistent with the Lewis structure? Yes, it is. Gross. It is. Yeah, so MO theory, it's the strongest of all the theories. Okay, it's the hardest, but it's consistent with everything. And yeah, that's gross. Okay, so let's keep going. All right, so we did it in hydrogen. We just combined 2 s orbitals. Let's do the same thing for helium. Helium has a electron configuration of 1s2, 2 electrons in the 1s orbital. So we are still combining s orbitals. So we have 2 s orbitals, they combine, sigma star. Same, so we're using the exact same MO diagram for hydrogen than we are for helium, diatomic helium. So I'm going to have a box down there, a box up here, sigma star. But the difference, I use the same diagram, but the difference is how many electrons I place. So for diatomic hydrogen, I place 2. How many electrons do I need to replace in the center for diatomic helium? 4, because 1, 2, 3, 4. So let's do that. So we go 1, 2. Where do the next electrons go? 3, 4. Cool. So let's calculate the bond order for diatomic helium. How many electrons in bonding orbitals? So we only count the electrons in the center here. Remember, these are atomic orbitals on the outside. So how many electrons in bonding? 2 minus antibonding. 2 over 2 equals 0. What does that mean, 0? bond order of 0. Is there a bond? No. So do you think diatomic helium exists? No, it doesn't. But doesn't that make sense? Helium is a noble gas. Is helium going to form chemical bonds? No. All right. So diatomic helium does not exist because the bond order is 0. What about the bond order for diatomic helium cation? How would you do that? How would you do that? A cation is what? A substance that loses an electron. So to make the cation MO diagram, you always start with the neutral diagram, and then what do you think we'll do? Remove an electron. So which electron do you think we remove? The first one, the top one. We want to remove the top electron, the topmost, right? The top of the bucket, just like before, all right? We're always removing highest energy electrons. So in this case, it's the anti-bonding electron. So if you calculate the bond order for this helium diatomic molecule, what is it? It would be a half. It's 2 electrons in bonding, 1 in anti-bonding over 2. It's a half. Bond order of 1/2. So in theory, this molecule, diatomic helium cation, theoretically can exist because we're removing an electron, and that just so happens the electron we're removing is from an anti-bonding orbital. So we actually strengthen the bond if we remove an electron from anti-bonding, but if we add an electron to anti-bonding, we weaken the bond. And you can see that mathematically, right? If we add an electron to a bonding orbital, what do we do to the bond? Strengthen it. But if we remove an electron from a bonding orbital, we weaken it. And you can see that from the equation, right? Because it's bonding minus anti-bonding over 2. Okay, all right. So that is hydrogen and helium. Oh yeah, you can also, we can write electron configurations for atoms. So like 1s1, right? An electron in a 1s orbital on a hydrogen atom. We can also write electron configurations for molecules. So we do the same thing, but we want to tell the reader what molecular orbitals are our electrons in. So for hydrogen, we would say, oh, it's molecular, the electrons in the molecule are in a sigma 1s orbital. There are 2 electrons in it. And that would be it. There's no electrons in the stars, so you don't have to write anything. And this is a nice way that you can calculate bond order easily if you have the whole electron configuration written out here. All right, so let's write the electron configuration for helium. So diatomic helium would be sigma 1s2. Where are the next electrons? Sigma 1s star. We need a star there because the next electrons up would be sigma star. And then there are 2 electrons in there. Okay, so we're just saying exactly where the electrons are at, but in the molecule. All right, so let's, review orbitals. Because I say orbitals a lot, and I talk about a lot of different orbitals, but not all the orbitals are the same. And so I want to just take some time now that I've introduced every single type of orbital you can imagine, I want to review all of them, all right? So we actually talked about 3 main types of orbitals in this class, and I think the symbols we use to show what they are clearly indicate what kind of orbitals they are. So the first one we talked about in chapter 6, atomic orbitals, S, P, D. Those are electrons that are on atoms, atomic orbitals. A 2s1, that's a electron in a 2s orbital. So if that's a valence electron, that's probably lithium or something like that, right? Because that's an atom. S, P, D, that's atomic orbitals. Okay. Once we, get a little bit more complex and have to start making shapes, all right, we have to now combine atomic orbitals to get those new shapes. So when we mix atomic orbitals, that's what we call hybridization. And so that's when I talk about hybrid orbitals. So hybrid orbitals are things like sp, sp2, sp3, all right? So you can clearly see in the name, hey, you mixed a bunch of atomic orbitals together, that's a hybrid orbital. That's related to valence bond theory and what explains all of our shapes that we can get, right? Is that what I said? Yes, okay, combining atomic orbitals. Now, All right, those are all on atoms, okay? So even hybrid orbitals are on atoms, but it requires mixing. So now these new orbitals, molecular orbitals, these are orbitals that arise from orbitals on two atoms overlapping. You have to have two atoms involved, so they're interactions, all right? So typically like two orbitals, either atomic or hybrid, have to combine to overlap. That's a molecular orbital. So since things are overlapping, we need to think about our second, our secondary, our Greek alphabet, pi, sigma bonds. So when you see symbols like sigma, sigma star, pi, those are molecular orbitals because they're between molecules because you have orbitals interacting, right? Yeah, so that's what you see. That's why we see the Greek alphabet here. So we see sigma, meaning there's 2 electrons in our sigma bonding orbital, 2 electrons in our sigma 2s bonding orbital. Just that 2s means that that sigma interaction is between 2s orbitals instead of 1s. Star for antibonding, and then we'll soon here look at pi interactions too. Okay, so with that in mind, I just reviewed it. What 2 atoms am I showing you right now? Get a hint from how the electrons are labeled. It says 1s, 2s. So these are atoms, right? S means atom, right? So this diagram is trying to show you, oh, this thing has 2 electrons and it's 1s, 1 electron and it's 2s. What element is that? What atom is that? Lithium. So both of them, we have 2 lithium atoms. Yes. Those are the 2 atoms we're combining, lithium and lithium. So in the center, we're going to have the molecule. So what's our molecule? I know it's weird. It's diatomic lithium. So diatomic lithium. We're making a bond between lithium, but we want to understand a little bit more about it. All right, so when s orbitals overlap, what kind of interaction is there? What is this? It's sigma. So if I combine 2 atomic orbitals, how many molecular orbitals do I get out? 1. Okay. Do you remember from hybrid orbital theory? The number of atomic orbitals equals the number of hybrid orbitals you get out. It's the same thing here. If you combine 2 atomic orbitals, you get 2 molecular orbitals out. Okay? So we get a sigma bond and we get a sigma antibond. So those are our 2 orbitals, right? Those are the rules of linear combinations because that's essentially what we're doing. So we get a sigma, okay, sigma bonding orbital between 1s orbitals, and then we get a sigma star between 1s orbitals. There we go. So the star antibonding is always higher in energy. There we go. So that's that one interaction. Well, what about 2s orbitals? Put your scientist cap on. How is a 2s orbital different than a 1s orbital? It's just bigger. So let's just think about it. Okay, so there's my bigger 2s orbitals. What kind of interaction is that? Sigma. So what do you think the MO diagram will look like between these 2s orbitals? Just the same, right? It's just going to look the exact same. Yay! Not too bad, right? So we have our sigma. It just so happens to be between 2s, and then we have another sigma star, and it's between 2s. So there we go. There's our other interaction. Beautiful. Okay, so now that I have my diagram, the s orbitals combined, we got a sigma and sigma star. For fun, count how many total atomic orbitals there are drawn on this page. 4, how many MOs total are on this page? How many molecular orbital boxes? 4, yes, because you combine 4 waves, you get 4 waves out, always. All right, what do we do now? What? Yeah, you place electrons. Yeah, we haven't put any electrons in yet. Do we know how many electrons we have to place in the middle? Yeah, 4, wait, 5, 6. There's a total of 6 electrons. 1, 2, 3, 4, 5, 6. So 6 electrons. Okay, where do we start filling? Bottom up, yes, okay. So 1, where does the next electron go? Spin down, just like before. Use your intuition from like before, okay? 1, 2, 3, 4, 5, 6. Here we go. So let's calculate bond order. So note where each of those electrons are. So these electrons are in bonding orbitals. These electrons are in bonding orbitals, so it's 4 minus how many electrons in antibonding orbitals? 2 over 2. So the bond order is 1. Okay, so when calculating bond order, you're just looking at the center, all right? Because we made the molecule, then we can at basically that point ignore the atoms on the side. All right, so the bond order in diatomic lithium is 1. Beautiful. Okay, so does it exist? Yes, according to MO theory. Okay, so let's determine the bond order in lithium. So we already did it in that one. So 4 minus 2 over 2 equals 1. What about the lithium cation? What do we do to make the lithium cation? We remove an electron. Any electron? No, the topmost electron. So we are removing this electron. Note what kind of orbital it's in, or what kind of molecular orbital it's in. It's in a bonding orbital. So without doing the calculation, are you going to strengthen or weaken the bond if you remove an electron from a bonding orbital? Weaken the bond, yeah. So you will weaken the bond, but let's calculate it anyway. So to make the cation, you literally you start with the neutral atom or molecule and you just remove that electron, the appropriate charge. So the new number of bonding electrons, it's 3 minus 2 over 2. So the bond order is a half. Cool, all right. So what about the lithium anion? Now we need to add an electron to the MO diagram. Where do you add it? Where's the next available spot? Anti-bonding. So without doing any calculations, if you add an electron to anti-bonding, will it strengthen or weaken the bond? Weaken, yes, but let's check it for real. If we add an electron to anti-bonding, the new calculation will be 4 minus 3 over 2, and you get a bond order of a half. So it matches exactly what we predicted, right? So cations and anions are good. As long as you can form the neutral molecule, that's the hard part. You can add or remove electrons as needed, right? And so lots of questions can arise here from bond order. If we ask you, okay, like what's the bond order in these things? We can also ask you in terms of, okay, which bond is strongest? Which bond is weakest? That relates to the same bond order trends we talked about before. Or we can talk about bond length. I could ask, which of these molecules has the shortest bond? And which one would you say? Which one has the shortest bond? Lithium, the diatomic lithium, because that's the highest bond order. So lots of ways to ask literally the same question relating to bond order. Cool? All right, so in this example, we combined s orbitals. We get sigma, sigma star. Now this is where things get complicated, where we have to now think about p orbitals. So if we are trying to make a diatomic boron or something, right? Each boron atom has 3 p orbitals. 3 p orbitals. So if each boron has 3 p orbitals, 3 p orbitals plus 3 p orbitals, when they interact, how many molecular orbitals will you get out? 6, yeah, so we need to account for 6 different molecular orbitals between p orbitals, and here they are. The first interaction is sigma. It's a sigma bond. If you think about pz orbitals, all right, if they're on the internuclear axis, they can overlap in that head-on fashion, the first set. All right, so you can get the first interaction is sigma between p orbitals, p atomic orbitals. The next 2 sets are side-by-side interactions, 2 sets of pi interactions. All right, those are between your px and your py adjacent orbitals. So these are your pi interactions. And I should have mentioned here with our pz orbitals doing your sigma interaction, you get a sigma and a sigma star. So there's our sigma star. And then for our p interactions, you get 2 equivalent sets, 2 sets of pi and pi star. So here's your pi. there's your pi star. So these are equivalent. So there's two equivalent molecular orbitals in each of them. And so putting it all together, you get this ordering where it goes 1, 2, 2, 1, where it goes sigma, pi, pi, pi star, sigma star. So I always remember that the pi's are in sets of 2s, and then you're good. But just to put a little wrinkle in everything, some of the elements, this is why there's 2 diagrams, the ordering is slightly different for what I call light period 2 elements. It goes pi, sigma, pi star, sigma star, and then the heavier period 2 elements goes sigma, pi, pi star, sigma. So basically these 2 orbitals, the first 2, these 2, they just swap places. But the great thing is you don't have to memorize it. You just have to know that here, when it's a set of 2, it's pi. When it's a set of 1, it starts at sigma. And so we'll do some examples on Monday going over this. So this means that homework for Chapter 9 isn't due until after the midterm, but I do encourage you to try it because it's extra practice and you can earn points along the way.